Okay, it works now. All right, in this exercise, you are asked to say, if you are asked to find xt and pt, we can go directly uh, to the Hamilton's equation to find the x dot t and p dot t, and then solve these two differential equations, coupled differential equations, right? And you can get the final results. But the purpose of this exercise is, is not just xt and pt. I would like you to explore the time evolution, or any other functions which you are interested in. All right. Okay, let me go through it once again. So if you are only interested in xt and pt, this is the way to do it. We're given the Hamiltonian, then we obtain the Hamilton's equations as shown in equation 5 and 6. Okay, as shown in equation 5 and 6. Okay, so x dot t is equal to the Poisson bracket between x and h. Then we apply the definitions. The first term contains a product of two partial derivatives, rank x, rank h, rank p. And this will give us p over m. The second term, the second term involves the rank x, rank p, and that is equal to 0 because x and p are independent variables. So finally, we have x dot equal to p over m. How about p dot? P dot is equal to the Poisson bracket between p and h. We plug in the definitions of the Poisson brackets. Then we get minus m omega square x. All right. Now, then we have a system of two coupled first order differential equations. Combining them, we obtain the first equation, x double dot equal to p dot over m, right? P dot over m is equal to minus omega square x. So this is a second order differential equation in x. And we know that it is the standard differential equation, standard equation motion for a simple harmonic oscillator. And the general solution will involve cosine omega t and sine omega t. Okay. And how about the pt? Once the xt is found, pt is equal to mx dot. So we just differentiate the xt and we can obtain the pt. Now we have two arbitrary constants, and these two arbitrary constants can be fixed by imposing the initial conditions: x at t equal to 0, p at t equal to 0. Okay, so imposing the two initial conditions, we determine the two arbitrary constant c equal to x naught and d equal to p naught over m omega. As a result, we have determined the xt and pt as time evolves. Right? You can see that it exhibit harmonic oscillations, periodic motions. Now, alternatively, if we are interested in x and p, and somehow we have never we do not we don't care about the definition of the Poisson bracket, but we know the arithmetics of the Poisson brackets associated with the Poisson brackets. All right. So the Poisson bracket between x and h, how can we determine it? we apply the distributive law of addition or for the Poisson bracket. So we have two terms instead. All right, the first term between Poisson bracket involves the Poisson bracket between x and p squared over m. The other one is involves a Poisson bracket between x and also the potential energy, Vx. We can factor out the constants from each of these two terms. And finally, we are left with a Poisson bracket between x and p squared, and also a Poisson bracket between x and x squared. And we can expand it, distributive law of multiplication. Then we have four terms altogether, all right, as shown in here. Now, we know the fundamental Poisson brackets between x and x, p and p, and also x and p. These are the fundamental Poisson brackets that we are given, all right. Besides that, we know nothing. We know nothing about the definition, for example. Okay, in that case, we still can evaluate the Poisson bracket between x and h. Here, the Poisson bracket between x and x equal to 0. Poisson bracket between x and x equal to 0. Poisson bracket between x and p give you 1. All right. Poisson bracket between x and p give you 1. So we have two terms equal to 0, and also two identical terms, non-vanishing identical terms. And combining these two non-vanishing identical terms, we have p over m as the result of the Poisson bracket between x and h. All right. Here we have not applied the definition of Poisson bracket. We just know the fundamental Poisson brackets between x and p and x and x and p and p. All right. And the arithmetics of the Poisson brackets. We can do the same thing for to determine the Poisson bracket between p and h. So we plug in the definition of h and then apply the distributive law of addition, and then factor out the constants, and then apply the distributive law of multiplication, and apply the fundamental Poisson brackets between xp, xx, and xpp, all right? And then we collect all the like terms, and finally, we know that we can, we realize that the Poisson bracket between p and h is equal to minus m omega squared x. So again, we obtain two coupled first order differential equations, all right? Okay, and then we have to solve the two coupled first order differential equations as shown before, as shown in equation 5 to equation 9, equation 11. Okay, so there are two ways to determine the Hamilton's equation. However, if we are not interested in determining x and p only, you're interested in determining some functions of x and p, all right? Then what can we do? First step, we repeat, we just go through all these steps here to determine x and p, and then plug in the definition of the function that you are interested in. For example, a and a star. Once we know xt and pt, we know at and a star t, right? However, if you might ask, is it possible to determine at and a star t without going through the previous procedures, i.e. determining xt and pt first? The answer is yes, because the Hamilton's equation tells us that any function of x and p will obey Hamilton's equation. So we know that the A will obey the Hamilton's equation, A dot equal to the Poisson bracket between A and H. That is the Hamilton's equation for this function A, all right? Now, before going directly to evaluate the Hamilton's equation of the function A, I would like to show you that the function A and the function A star has a very interesting Poisson bracket. All right, the Poisson bracket between A and A star can be determined in the following. We plug in the definitions of these two functions, factor out all the constants, and then apply the distributive law, all right, of the Poisson brackets. Then altogether we have 4 terms, all right? Now, Poisson bracket x and x, between x and x equal to 0, between x and p gives you 1, between p and x gives you -1, between the Poisson bracket between p and p gives you 0, all right? And then we connect the like terms, and we find out that the Poisson bracket is very simple, equal to -i, okay? In other words, the A dot there's something, okay, -i. Then we, this is a very interesting property. Later, when you study quantum physics, and you realize that in the case of quantum simple harmonic oscillator, you have corresponding counterparts of these two functions. A corresponds to the so-called lowering operator, A star corresponding to the raising operator, and they obey a very simple quantum computation relations like this. All right. So as I said before, the arithmetics of Poisson brackets is very similar to, or very similar to the arithmetic of quantum commutators. All right. Now we move forward to determine the AT. Now the Hamilton's equation of AT is given here. A dot equal to the commutator between A and H. All right. Now there are 2 ways to do it. One, we apply the arithmetics of Poisson brackets, or the other one is to apply the definitions of Poisson bracket. All right. Here, since H is expressed in terms of x and p, so it's better to apply the definition of Poisson bracket. All right. Okay. The first term involves the partial derivative of A with respect to x and partial derivative of h with respect to p. As shown before, the partial derivative of h with respect to p gives you p over m. And according to the definition of A, if we differentiate A with respect to x, we get a constant square root m omega divided by 2, all right? The second term involves the partial derivative of A with respect to p, and also a partial derivative of h with respect to x. And you can evaluate these 2 terms easily by plugging in the exact formula of the exact definition of h and also exact definition of A, all right? So we get this. After simplification, going through all these small steps, then we realize that, wow, it's very nice. It is equal to -i omega A, all right? Then you ask, how about the Hamilton's equation for A star? We know that A star is the complex conjugate of A. Once we know A, then A star can be obtained readily. All right, and so we don't have to really worry about it for the time being. And we look at this equation 18. It is a single first order differential equation involving A only. It does not couple with A star. Okay, so we can immediately find AT by solving this first order differential equation. All right, and we know that this first order differential equation must have a solution in the form of an exponential function. Why? Because you differentiate A once and you get back something proportional to itself. So what kind of function, what kind of solution can it be? Exponential function. All right. So the solution is AT equal to A at t equal to 0. This is the integration constant or the arbitrary constant of integration time e to the power minus I omega t. All right. What is A at t equal to 0? We can express it in terms of x at t equal to 0 and also p at x equal to 0 at t equal to 0, i.e. the initial conditions. All right. So we find the AT. A star t, very simple. Taking the complex conjugate, we get A star t. So we can find the AT and A star t right away. Okay. Now, if we don't want to apply the definition of Poisson brackets, we can just follow the arithmetics of the Poisson brackets as shown in equation 21. All right, we plug in the definitions of A and also the definition of H, and then apply the distributive law of Poisson brackets. Then we have 4 terms, and 2 of these 2 terms involving Poisson bracket between x and p, x and x, and the other 2 terms involve the Poisson bracket between let's see, sorry. These 4 terms has one Poisson bracket between x and p, and another one between the Poisson bracket between p and x, and also one between p and p, and the final one is between x and x. All right. So the Poisson bracket between p and p and the Poisson bracket between x and x give you 0. All right. And the remaining 2 terms are related to each other as shown here. And we can combine them together and find that the final result is equal to minus omega A. All right. So this is the exact results as shown before. But here we apply the arithmetics of Poisson brackets rather than the definitions of Poisson brackets. All right. So you can do either way. Both of them are equivalent. Okay. Now, in terms of x and x star, we can find x and p. All right. We have found AT and A star t. So we can obtain x star, xt and pt right away by reversing the definitions. All right, of A and A star t. So xt is given by this, pt is given by this. So a periodic solution. In terms of, we can also express the H in terms of A and A star t, all right? First of all, P squared over 2m, it gives you the kinetic energy, all right? So P square here over 2m. The potential energy is 1/2 m omega squared x squared. This is the definition of x squared, all right? So then we try to expand both terms and combine them, and we find a very surprising result. H is equal to, H is proportional to the norm square of A, or it is equal to the product of A star and A. all right? So this is a very, very interesting result. And now if we start with expressing H in terms of A star A, then the Hamilton's equation for A and A star will become very simple. Say here, A dot equal to Poisson bracket between A and H. All right. Now we plug in the definition of H, which is equal to omega A star A. All right. Then we apply the distributive law, and we can evaluate the Poisson bracket right away, which is equal to minus I omega A. Since we know the Poisson bracket between A and A star and also A and A. The Poisson bracket between A and A is equal to 0. Poisson bracket between A and A star gives you minus A, all right, as shown above. Now let us consider the special case M equal to 1, omega equal to 1, all right? And we can easily see that the magnitude of A is equal to square root of H, or H equal to the norm square of the complex variable A, right? All right. And since H is conserved, so the AT, the norm of the AT is also conserved. All right. So that means AT traverses along a circular orbit of radius. All right, in the complex plane X and IP. All right. This example tells us that an appropriate choice of dynamical variables will help extract useful information about a given system more easily. All right. Now, the complex plane XIP, which is commonly known as the phase space, offers a very convenient tool for us to explore some nonlinear systems. And you will learn more from the course Mechanics 2, all right? Okay, so far, any questions? So you know why I have gone through this exercise with you once again, because it is important to know that if you are interested in some functions of X and P, you don't have to go through solving or finding the xt and pt first. You can solve the Hamilton's equation associated with the function that you are interested in directly. All right. So that's the purpose of this example. Any questions so far? Any questions about this example? Now, as I said, you will, when you study quantum physics, you find this example very familiar later, all right? Because the only difference between classical mechanics and quantum mechanics is that the dynamical variables x, p, a star will become quantum operators. The Poisson brackets between these variables will become quantum commutators of the operators. All right. Right. When we go to the phase space, let me see. when we go to the phase space, we see a circle. All right, this the variable a will follow a circular path. As you can see here, in this example, the circular path means that the h is conserved. All right. What is the meaning of a? As shown here, the magnitude of a gives you the square root of h. All right. No, that is the magnitude of a. Okay, the norm a, because h is equal to a star times a. All right. You have a complex variable, complex number multiplied by its conjugate. All right, that gives you the norm square. Okay. All right. Let's look at another one. Now, there's an exercise about the Poisson's theorem. All right. Here, and also it asks you to determine the Poisson bracket between Lx and Ly. Okay. Now I show you how to do it here without going through the differentiation. Okay. Now, first of all, Lx is equal to ypz minus zpx. Ly gives you zpx minus xpz. And Lz equal to Lz equal to xpy minus ypx. All right. So we want to compute the Poisson bracket between Lx and Ly. Okay. So we plug in the definitions of Lx and Ly, and then apply the arithmetics of Poisson brackets. All right. I will answer the question of Dai-Chun He after finishing this example. All right. Lx, Poisson bracket between Lx and Ly will be evaluated via using the arithmetics of the Poisson brackets. Okay, we plug in the definitions of Lx and Ly here, and then apply the distributive law of the Poisson brackets. So we have 4 altogether. All right, and then apply the distributive law to each Poisson brackets. All right. So we know that Poisson bracket here for each Poisson bracket, it will involve 4 terms. Okay, 4 terms. However, the Poisson bracket between y and z equal to 0. Poisson bracket between vz and px equal to 0. All right. Poisson bracket between y and px also equal to 0. All right. So only one left, and that is equal to this. All right. Here, the second one, if you 0 Poisson bracket, because the 4 terms all vanish. The third Poisson bracket will also give you 4 0 Poisson brackets. The last one, similar to the first one, they give you only 1 non-zero Poisson bracket. All right. Then we combine the results, and we have xpy minus ypx. So we do have Lz. All right, the Poisson bracket between Lx and Ly give you Lz. So we go back to this exercise here now. Now, if Lx and Ly are both conserved quantities, according to the Poisson's theorem, then the Poisson bracket between Lx and Ly is another conserved quantity. And we realize that the Poisson bracket between Lx and Ly is equal to Lz. So in other words, all three components are conserved quantities, all right? Now we want to explore a little bit more. What are the Poisson brackets between any two of the components? Okay, so I runs from 1 to 3, and this is the definition of the angular momentum. All right, cross product R cross P. I use the Einstein summation convention and also express the cross product by using this totally anti-symmetric symbol, epsilon ijk. All right. Now we plug in the definition for Li and Lj. So the first one is epsilon ikl xkpl. The second one is epsilon jmn xmpn. Summation convention is assumed. All right, since these totally anti-symmetric symbols are basically constant, so we can factor them out, and we are left with the Poisson bracket between these two terms. And we apply the distributive law of the Poisson brackets and obtain 4 Poisson brackets, all right? The first one obviously vanishes. The second one gives you minus delta Lm, because if L not equal to M, then they have a 0 Poisson bracket, right? The third term gives you delta Kn. Finally, the fourth term gives you 0. So we apply the fundamental Poisson brackets, and we realize that they can be evaluated very easily. Okay. So 2 terms are left. All right. Now, we try to simplify these 2 terms. How? So we rewrite the totally symmetric, anti-symmetric symbols like this. Epsilon Kli, as long as we have cyclic permutation of the 3 indices, the value of this totally anti-symmetric symbol remains unchanged. All right. So the second totally anti-symmetric symbol is written as epsilon kjm. Right? We repeat the same thing for the second product of totally anti-symmetric symbols. Then we apply the identity that you are familiar with. The product of 2 totally anti-symmetric symbols with the Einstein summation convention over K. This product will give you this results. It is equal to this. Okay, we have this identity. We apply this identity to both terms. Then we have altogether 4 terms involving products of Kronecker delta function. All right. The first term will give you xipj. The second term will give you delta ij, xlpl. The third term gives you xjpi. The last term gives you delta ij, xkpk. Remember that we have Einstein summation. Here, xkpk means x r vector dot p vector. Same for here. R vector dot p vector, right? So these 2 terms cancel. Then we are left with this. By definitions, this is equal to epsilon ijklk. Okay. So finally, we have a very nice relation. The Poisson bracket between Li and Lj is equal to epsilon ijk Lk. All right. If I is 1, j is 2, then Lk will be 3. So Poisson bracket between Lx, Ly is equal to Lz. Poisson bracket between Ly, Lz give you Lx. Poisson bracket between Lz, Lx give you Poisson bracket Ly. All right, cyclic permutations. Now, we can also define some interesting functions like L plus, L minus in terms of Lx and Ly. L plus and L minus are complex variables, complex functions, all right, since we have a purely imaginary unit here. And we would like to compute some interesting Poisson brackets. The Poisson bracket between Lz and also L plus. Poisson bracket between Lz and L minus, and also Poisson bracket between L plus and L minus, all right? And we can easily see that L plus and is the complex conjugate of L minus, all right? So what is Lz, L plus? We plug in the definition for L plus, all right? By distributive law of the angular momentum of the Poisson bracket, we have two terms. The first term, Lz, Lx, so 3, 1, then we get the Ly, 2, right, L2. Here we have 3, 2, then we have minus Lx, according to the Poisson bracket determined here. Okay, determined here. Li, Lj gives you the epsilon ijk Lk. Okay, so we find that Lz, L plus gives you minus I, L plus. Similarly, we can do the same, we can repeat the same procedures. We realize that Lz, L minus give you minus I, L minus, okay? And how about L plus and L minus? What happened? So we plug in the definitions for L plus and L minus. By distributive law of the Poisson brackets, we have 4 terms altogether. And the first Poisson bracket gives you 0. The fourth Poisson bracket gives you 0. And the second and third give you minus ILZ, right? So we combine them together, we have minus I2LZ. Okay, so these functions of Lx, Ly, and Lz obey some very nice Poisson brackets. How about L square? Okay, that is equal to Lx squared plus Ly squared, Lz squared, all right? If we want to compute the Poisson bracket between L squared and Lx, L squared and L plus minus, what do we get? Li squared, Lj, okay, any one of the component. Then we just apply the fundamental relation between Li and Lj that gives you epsilon ijk Lk. And here we have Li, same for the second term. And we realize that these two terms are the same because the indices are dummy indices. So they are equal to each other. Then we have 2 epsilon ijk Li Lk, right? Now, if I switch the indices I and j, we get a minus sign, all right? However, since these are dummy indices, we can relabel them later, all right? So here, epsilon ijk, and then we perform cyclic permutations. Then we have kji, right? And then renaming I and k because they are dummy indices. Then we get back the epsilon ijk, Lk, Li, all right? Now this is exactly equal to the the Poisson bracket itself with a minus sign in front, okay? So how can we get such a result? A quantity equal to the minus itself. The quantity must vanish automatically, right? Now, obviously, we can repeat the same calculations for L plus and L minus, but we don't have to do that because L plus is equal to Lx plus ILy, since L squared commute with all components. So it must commute with, the Poisson brackets between L squared and each component equal to 0, then the Poisson bracket between L squared and L plus L minus must vanish automatically. Okay. So again, if you go to quantum physics later, you realize that the L angular momentum will become angular momentum operators. And these angular momentum operators will obey commutation rules, very much like the Poisson brackets shown here. All right, this is another example telling you that if you study analytical classical mechanics well, quantum mechanics becomes simple or becomes familiar to you. All the tools, techniques, ideas are very much like the classical mechanics. Quantum commutators is the counterpart of Poisson brackets. Quantum operators are the counterparts of the classical mechanics dynamical variables. Okay. Then the Hamilton's equation in classical mechanics will become Heisenberg's equation motion of the operators in quantum physics. So you can see the mapping between classical mechanics and quantum mechanics. So you can so the analytical mechanics give us the advantage of understanding quantum mechanics in a more straightforward way. Here's another question. Now the Poisson theorem states that if any two components of the angular momentum are conserved, then the remaining component is also conserved, leading to the conservation of the angular momentum. All right. Now, one may wonder if two of the components of a given function or given vector are identically 0, then the remaining component must be conserved. Why? Because the Poisson bracket between 2, 0 must be 0, right? For instance, in any motion confined to a plane, the components of the angular momentum in the plane are 0. So say, for example, planetary motion, the angular momentum Lx and Ly are 0. So the angular momentum is conserved because the third component is also conserved, is also equal to 0. However, there appear to be a number of obvious contradictions to this prediction. One particular example is an oscillating spring in a watch. Okay, so why is this so? Here is the answer. The confusion is due to the misunderstanding that having two components equal to 0 and having them conserved are equivalent. They are not the same, all right? The Poisson theorem requires that the two components must be conserved for any initial conditions, not constrained, okay? Not just put them equal to 0 at the very beginning, all right? So this is the key point. So having two components equal to 0 is not the same as having them conserved, all right? Okay, let me go back to Dai Chun Hei's question. So the form So the form of was just guessed by mathematicians. Not really. If we go back to the previous example, now here in equation 11, the Hamiltonian function is written in terms of p squared and x squared. All right. Now, we know that the x and p are independent variables. Sort of like we can construct a coordinate system. The horizontal axis is x, the perpendicular axis is p, right? So we can identify h for each values of x and p, okay? Now, we would like to ask, is it possible to define some complex variables, okay? Complex variables in terms of x and p, just like the complex plane. We have a complex variable, and each complex variable is equal to x plus iy, right? We can just do the same thing. And also, you will learn later that you ask yourself, is it possible to rewrite the sum of two terms here as a product, all right, as a product of two functions, okay, two complex functions? And the answer is yes, okay? Why do I say so? Because h is real, as we know. If we write them in terms of two product of two complex functions, then the two complex functions must be complex conjugate to each other. All right, so this is very obvious. Okay. Ying Chen, why AT, absolute value of AT equal to absolute value of A naught? Okay. Now here, we solved the equation already, right? The A dot equal to minus I omega A. So it is an exponential function, all right? Exponential function for the solution. And if we take the absolute value of AT, both sides, this is an exponential function involving a phase factor, right? This is an exponential function of a phase factor. So if we take the absolute value, it must be equal to 1. So that's why the absolute value of AT equal to absolute value of A naught, okay? Because this is a phase factor only. If we take absolute value of a phase factor, it is equal to 1. If you don't believe me, then you write it down. This is equal to cosine omega t minus sine omega t, right? And you take absolute values of this term, then you will have cosine square omega t plus sine square omega t. Okay, and we know that it must be equal to 1, right? Cosine square of an angle plus sine square of the same angle must equal to 1. All right. So this space, the absolute value of this space factor must equal to 1. That's why we have this final results. Oh. Okay. All right. Okay, how about let us take 5 minutes break and then we'll come back. All right, 5 minutes break. If you have any questions, let me know. Five minutes break. Okay, here are some more examples about Poisson brackets, Hamilton's equation motion, right? All right, first example, simple harmonic oscillator again. Now, if we are not interested in finding the xt and pt directly, if we are interested in finding the time evolution of the kinetic energy and also potential energy, then what should we do? First step, the first approach, find PT and XT. And then based upon PT and XT, we can determine the kinetic energy and potential energy, right? Now the Hamilton's equation give us an alternative. Before doing that, let us consider three variables. First one, K plus, second one, K minus, the third one, K naught, all right? Now we want to evaluate their Poisson brackets. First one, K plus and K minus, okay? The Poisson bracket between K plus and K minus. We substitute the definition of K plus and K minus. Factor out the constant first, then we are left with the Poisson bracket between K square, P square. Then we apply distributive law. We have this and evaluate X and P square, all right? Then we apply the distributive law again. So we have 2P for this Poisson bracket. So we find that all two Poisson brackets give you the same answer. And we double check with the definition of K naught. And we realize that this final results is equal to, can be written as I2 K naught, all right? And how about the Poisson bracket between K naught and K plus? Again, we plug in the definition first, K naught, K plus, okay, factor out the constants. We get this. Apply the distributive law of the Poisson brackets, okay, and simplify. We have this, all right. So we realize that the Poisson bracket of K naught between K naught and K plus give you minus IK plus. How about K naught and K minus? We repeat the same kind of calculation. We realize that it is equal to IK minus. Okay, so we can summarize. K plus K minus give you I2 K naught. K naught K plus give you minus IK plus. K naught K minus give you IK minus. All right, these are the fundamental Poisson brackets between these three functions. Now we can also see that the Hamiltonian function can be written as minus IK plus divide time m omega square, right? Minus I K minus divided by m. So the Hamiltonian function can be expressed in terms of k plus k minus 2. Okay, so we want to look at the Hamilton's equation of k naught. So k naught dot equal to the Poisson bracket between k naught and h. Since h can be expressed in terms of k minus k plus, so we can evaluate the Poisson bracket directly by substituting this definition of Hamilton function into the Poisson bracket. And then we apply the distributive law of Poisson brackets. The first Poisson bracket will give you I k minus. The second Poisson bracket will give you minus I k plus. All right. And then we simplify. We get this. Poisson bracket between k plus and h give you 2k naught over m. So k plus dot equal to 2 over m k naught. How about k minus dot? Give you the Poisson bracket between k minus and h equal to minus 2m omega square k naught. All right. So we have the Hamilton's equation of k naught, k plus, k minus all together. And we realize that they are coupled to each other, right? They are coupled to each other. Okay. Now, say we don't want to solve a set of three coupled ordinary differential equations, first order ordinary differential equations. We have never learned first order differential equations before. So what can we do? We can go through this simple arithmetic. We know that Tt, the kinetic energy, is equal to minus I over m times k minus. Potential energy is related to k plus t, all right? And this is the initial condition, okay? Since x naught equal to 0, p naught is given here, the initial condition. So how about the kinetic energy at any time t? We can apply the Taylor's expansion. This is the first derivative at t equals 0. This is the second derivative at t equals 0, right? So what we can do is just keep evaluating the Poisson brackets, higher order Poisson brackets, all right? Based upon the fundamental Poisson brackets between k plus, k minus, k naught. So the first Poisson bracket, t between t and h, is proportional to the Poisson bracket between k minus and h. So we get I2 omega square k naught, all right? If we evaluate it at t equal to 0, what do we get? We get 0. Why? Let us go back to here, k naught at t equal to 0. What is k naught? Here. At t equal to 0, we know that at t equal to 0, x equal to 0. All right, so k naught equal to 0. So the first Poisson bracket between t and h equal to 0 at t equal to 0. And then the second order Poisson bracket, that means the first order Poisson bracket between k naught and h, all right? And this Poisson bracket is proportional to k minus. The first term is proportional to k minus. The other term is proportional to k plus, all right? At t equal to 0, what happens? At t equal to 0, the first term will survive, but the second term will vanish, all right? So, and we realize that this term is proportional to the initial value of the kinetic energy, all right? How about the third order Poisson bracket? We repeat the procedure. Since we have two terms from the second order Poisson bracket, then we have two terms in the third order Poisson brackets involving k plus and k minus. And we realize that after simplification, it is proportional to k naught. Again, at t equal to 0, k naught equal to 0. So this equal to 0. And we keep doing it, all right, keep doing it basic, and you can evaluate the kinetic energy as a function like this. Okay, so so you don't have, even though you do not know anything about solving a set of coupled first order differential equations, you can still do something to get some approximate solutions, right? If you're hardworking enough, you can keep doing it, keep expanding it, keep collecting more high order terms, okay, in this series. How about the potential energy? We repeat the same thing. Evaluate the Poisson bracket between H and X, V and H, okay, and the high order Poisson brackets too. As shown here, after straightforward procedures, we realize that the VT can involves series, power series of T, okay, and which is related to the kinetic energy, all right, as shown here. It is related to the kinetic energy, all right, and so in this way, we find approximate solution to kinetic energy at time t and potential energy at time t, all right? What we need to do is keep evaluating higher and higher Poisson brackets, all right? Now, let's go back to the exact solutions. Solving, we know that given the simple harmonic oscillator Hamiltonian, the solution PT and XT are given by this, given the initial condition. So the kinetic energy is equal to P squared over 2T. So that is equal to cosine square omega T. Vt is proportional to sine square omega T. Now, if we take a closer look at cosine square omega T, the first few terms are given here, and sine square omega T, the first few terms are given here. And they coincide with what we got from the systematic evaluation of higher and higher Poisson brackets using the Taylor series expansion, all right, in T. So in fact, it is a good way to obtain the exact results via the Taylor expansion in T. Okay. The second example, a simple pendulum. First of all, we identify the coordinates of the mass, x coordinate, y coordinate, x dot equal to this, y dot equal to this. So these are the velocities. Having known the velocities, we can write down the kinetic energy. Having given the coordinates, we can write down the potential energy. All right. Now, since x, there is a constraint relation, x squared plus y squared equal to L squared. All right. So, in fact, there is only one generalized coordinates, i.e. theta, all right? So Lagrangian can be written as 1/2 ml squared theta dot square plus mgl cosine theta. And we can immediately write down the Euler-Lagrange equation of motion, theta double dot equal to minus g over L sine theta, all right? So this is the Euler-Lagrange equation of motion. How about the Hamilton's equation? We define we figure out the generalized coordinate corresponding to theta, round L round theta dot, which is equal to ml squared theta dot, all right? After H is equal to P theta, theta dot minus L, right? Substituting this definition for P theta, we can rewrite the Hamiltonian as this, okay? Then Hamilton's equation is given here. Now, it is unfortunate that both Euler-Lagrange equation motion and the set of Hamilton's equations cannot be solved analytically, cannot be solved easily, all right? So what can we do? Pullman's method, all right, Pullman's method, because we have never learned how to solve complicated differential equations. So, but we know how to do the arithmetics of Poisson brackets, all right? So we just go ahead. Theta t is equal to theta naught plus t time the first order Poisson bracket evaluated at t equals 0 divided by I1 factorial. And then the second term involving the second Poisson bracket, second order Poisson bracket evaluated at t equals 0. The third term involves the third order Poisson brackets, right? Keep doing it. So the first order Poisson bracket between theta and h, what will we get? Theta and p theta, right? Remember that this is the theta is the generalized coordinate and p theta is the generalized momentum. Then they have the fundamental relation between x and px, all right? X and px. Okay, you can double check by evaluating xpx, ypx, and then figure out the theta and p theta, all right? Okay, if we are hardworking enough, we evaluate all these Poisson brackets, we finally stop at the order T4, okay, we get this. And how about P theta T? Do the same thing and stop at T4. Given the initial conditions, we realize that theta T is equal to theta naught minus T, a term proportional to T squared. P theta T, the leading order term is proportional to T, the second term proportional to T cubed, all right? Now, these are the approximate solutions to the problem. They are particularly good for short time period. So if we are interested in the time evolution of theta and p theta within a short time period, then these two expressions is good enough, all right? If you want more accurate results, then go one step further to obtain the T4 and go one step further to obtain the T5, all right? So the accuracy depends upon your effort, okay? Now, some smart students will tell me that, Professor Low, actually, we can apply the symbolic calculations using Mathematica, MATLAB, to do all these calculations for us. Then it will be trivial to obtain nth order Poisson brackets, okay? So you can go up to any order you like by pushing a button. All right, another, the final example, an harmonic oscillator. The potential energy has a one more term, that is that term proportional to x to the power 4, all right? So we write down the Lagrangian and also the Euler-Lagrange equation motion. Again, it's hopeless to solve this equation analytically, all right? We do not know how to do it. How about go to Hamiltonian mechanics? We realize that the set of two coupled Hamilton's equation basically are equivalent to the Euler-Lagrange equation motion. So what can we do? We are hardworking people. We don't want to give up no matter what. So use the poor man's method. Once we know the Hamiltonian function is given here, we keep doing the arithmetics, the Poisson bracket between x and h, p and h. Okay, keep doing it. Then we find that the first order Poisson bracket between x and h gives you p over m. The second order Poisson bracket between x and h gives you this. All right. Third order, fourth order, keep doing it. Then evaluating these Poisson brackets at t equal to 0. All right. Then we get a power series solution for x up to t cubed. Up to t cubed. If we are hardworking enough, we can go up to t to the power n. All right. Similarly, we can do the same thing for pt. So we have a power series solution for xt and pt in this way. And all the arbitrary constants are well determined. Here we have x naught and p naught being incorporated into the solution right away. Okay, so you can see that knowing the Poisson brackets arithmetics enables us to obtain approximate solutions for some difficult problems in classical mechanics. All right. Okay. So far, any questions? So that's why some of you ask me, do we need to know very well about the second order differential equations to work on problems in mechanics, research problem in mechanics? My answer is that it depends. All right. If you don't want to do complicated numerical calculations for solving second order differential equations, you only want to get some approximate solutions using arithmetics, then this is the way to do it. All right, this is the way to do it. Very much like the multiplication tables. All right, before we go, I have some online exercises for you. I hope you can try work it out. Okay. You can all see it, right? Question 1, a point moves in a vertical plane along a given curve in a uniform gravitational field. The equation of the curve in parametric form is x being a function of s. S is the length, arc length of the trajectory. Z is a function of the arc length. So write down the Euler-Lagrange equation of motion. All right. So how about I give you 5 minutes to get the answer, to write down the Euler-Lagrange equation of motion. All right, just write down the equation. You don't have to solve it. 5 minutes. Then I will ask someone to show us how to do it. All right. Now, to tackle this kind of problems, what you need to do is follow the recipe. Write down the coordinates, write down the Cartesian coordinates, write down the velocities, and then find the kinetic energy, find the potential energy, all right? And then the Lagrangian. Finally, express the Lagrangian in terms of the generalized coordinates and generalized velocities. Final step, write down the Euler-Lagrange equation motion in terms of the coordinate, the generalized coordinates and generalized velocities. Just step by step. There's no tricks. Just hard working. Step 1, step 2, step 3, step 4. Keep working on it, then you get the answer. Okay, 5 minutes.